We'll get started then. Okay, so we left off on Monday. I wanted to just kind of show that, theoretically, using the Metropolis algorithm or the Metropolis Hastings algorithm will produce a Markov chain whose stationary distribution is equal to the target distribution. Okay, that's what we wanted to show. And the way we're going to show this is by showing that when we have detailed balance, we have reached the stationary distribution. Okay, so on Monday we wanted to show that creating a Markov chain via the Metropolis algorithm or Metropolis Hastings algorithm will result in a chain whose stationary distribution is equal to the target distribution. Okay, and we will demonstrate this by showing that there's detailed balance when when the values follow the target distribution. Okay, and detailed balance is the idea that the amount flowing from A to B is equal to the amount flowing from B to A, okay, for any pair of states, okay, for all pairs of possible states. So we can show that the probability of going from one state to another state is equal, or not just the probability, the amount that flowing from one to another and flowing back the other way, if that's equal for every single possible pair of states, of which there might be an infinite number, then we have detailed balance, and that is going to be our stationary distribution. Okay. So again, we said the transition probability is transition to go to k plus 1, given that we're at x at k. This is the probability of transitioning from x at time k to x at time k plus 1, and if there's detailed balance, then this will be true, okay? Okay, and we said, you know, whenever you propose a value, x prime, we could either reject it or we might accept it. And on Monday, we showed that if we reject it, then x at time k plus 1 is going to be equal to x at time k. And so showing that there's detailed balance when the next, if the, you know, the other state that you're talking about is the state itself is trivial. Okay, so on Monday we showed that. So today we're going to show that the relationship still holds if we accept the proposed x value. Okay, so we can either accept or reject a proposed value x prime. Okay, if we reject it, then x at k plus 1 is equal to xk, and detailed balance is trivial. And this is shown in Monday's notes. Okay, so now we just have to kind of show we will still have detailed balance when x at k plus 1 does not equal our current x, okay? If our transition probabilities are set up using the Metropolis algorithm. Well, Metropolis Hastings algorithm. And then if it's true for the Metropolis Hastings algorithm, it's going to be true for the Metropolis algorithm, because the Metropolis algorithm is just a special case or a simplified version of the Metropolis Hastings algorithm where the Q distribution is symmetric, okay? So I guess I'll just write that. If it is true for Metropolis Hastings, then it works also for Metropolis. Metropolis algorithm, okay? Metropolis algorithm is a, quote, special case where the proposal Q of xk plus 1 given x at k is equal Q at x k given xk plus 1, okay? So we don't, so if it works there, then that's what we have. Okay, so the transition probability, all right, so with the Metropolis Hastings algorithm, okay, our transition probability is going to equal basically the probability of proposing a value times the probability of accepting the proposed value. Is that okay? So we're going to say the transition probability of going to location k plus 1, x at k plus 1, given that we started at xk, is going to equal the probability of proposing a value. So it's going to be, we have to propose xk plus 1 given our current location, multiplied by the probability of accepting that proposed value, which is going to be the minimum between 1 and the, using the target distribution, the proposed value given our current value. Okay. And then for the Metropolis Hastings algorithm, we have to include this thing. If you're just doing the Metropolis algorithm, then this part just simplifies to 1. This Q over Q stuff will just cancel out to just be 1. Yeah. Okay, so this is the probability of transitioning is equal to the probability of proposing the value times the probability of accepting the proposed value. Which we often call I often call this P move or whatever. Okay, but it's the probability of accepting the proposed value. All right, is that okay? All right, and so if I distribute this around, okay, then we're going to have x at k plus 1 given x at time k is equal. And what I'm going to do is I'm going to replace 1 with probability of x times k divided by probability of x k. All right. So I'm going to just replace 1 with this. Just do that here. Oh, sure. Okay. Okay, and so so this will become the minimum of, all right, and I'm going to just move some terms around here. Okay, so here the 1 is going to have p x of k over p x of k, and then I'm going to multiply this by q of x k plus 1 xk. All right, comma, so that's the first term. I've multiplied q of xk plus 1 given xk times 1, but I've replaced the 1 with p of xk over p of xk. All right, and that's this term over here. Is that okay? And then over here, I've got p of xk plus 1 over p of xk, all right? And then this term right here, xk plus 1, q of xk plus 1 given xk will cancel out with this term down here, okay? And so I will be left with q of xk given xk plus 1. Okay, so we'll, distribute q of xk plus 1 xk through the min function. Okay. All right, is that all right? And then I am going to extract out, I'm going to pull out 1 over p of xk out of both terms. Okay, so now I have minimum of p of xk times q of xk plus 1 given xk, and the other term is p of xk plus 1 times q of xk given xk plus 1. So the minimum between these two terms. All right, is that okay? So I just went from here to here, and I pulled this out. All right. I hope this is okay, but I'm going to just say using the same logic. All right. Okay. It can be shown that now I'm going to have the transition probability of going to xk given that we start at xk plus 1, okay? So basically, I'm just swapping the xk's with the xk plus 1. Okay, it's like just swap all of these terms, okay? And so what we're going to end up having is p of xk plus 1. So it's going to be exactly the same as this, but wherever you see an xk, you're going to replace it with k plus 1. And whenever you see xk plus 1, you replace it with xk, right? So I'm going to have minimum of p xk plus 1 q of xk q given xk plus 1. And then over here, I've got xk q xk plus 1 given xk. All right, it's a lot, I know. But is the arrival of getting these two things okay? This is kind of the transition probability if I write all of these things out. Okay, and so what we need to show is that we achieve detailed balance. Okay, so the Markov chain is defined by its transition probabilities, and what I want to show is that we have detailed balance when we apply the transition probabilities to the stationary distribution, okay? And in this case, the stationary distribution is the target distribution. So, or I guess what I want to show is that if I use the target distribution and I apply the transition probabilities to it, I'm going to get detailed balance, all right? So if we use the target distribution, which is just p of x, and apply the transition probabilities, we will have detailed balance for all pairs of points, or I guess pairs of states, xk and xk plus 1. Okay, so what I want to show is I need to show that the transition probability of going to xk plus 1, given that we start at xk, multiplied by the probability of being at xk, is equal to x going the other way, the amount going the other way, right? So if we have this, this is the condition for detailed balance, right? So this is a condition for detailed balance, and if there is detailed balance, then this would be the stationary distribution, okay? And if this is true, then P of x, our target distribution, is the stationary distribution. Okay, so basically I'm going to just copy this. I don't know how, am I able to do this? So I've got this thing. Can I copy this? Copy. So this is, all right, let me go back. Okay, so I'm going to take this entire thing. Let's, okay, so I'm going to copy this and come here. I'm going to paste this, and I'm going to shrink it down a little bit. Okay, so I've got that. All right, and I'm going to just go ahead and I'm going to, so this is the transition probability of going xk plus 1. So if I multiply this by P of xk, then I'll have P of x at k multiplied by the transition probability of xk plus 1 given xk is equal to, and I'm going to have P of xk multiplied by all of this, right? So I copy that, and I want to put that right here. Okay. And what do we have? Let me see. So these terms, this cancels with this, right? So now I'm just left with this min function. Okay. All right, and then let's do the other one. Okay. So now we will grab the other transition probability from up here. Okay, that's good. I come over here and we'll shrink this down. This is kind of fun. I don't know, playing around with this. All right, and then so I need to show that. So this is this term over here. So I've got to multiply probability of x at k plus 1 times this thing, xk given xk plus 1. And so I'll have probability of x k plus 1 multiplied by all of this over here. I just plug this in right there. Okay. And then, and what do we have? We'll have this term cancel with this. Okay, so all we're left is this is equal to this, and this is equal to this. And what do we notice? We notice is that this term is exactly equal to this term. And this term over here is exactly equal to this term over there. Okay? And so the probability of transitioning from one of, the amount flowing from x to k, or xk to k plus 1, and the amount flowing from k plus 1 to k is going to be the minimum of this value and this value. And the amount flowing the other way is going to be the minimum of this value and this value. But both of them are the exact same. You're using the same two values in that minimum function. So whatever it is, they are equal, okay? So these two things are exactly equal. Okay? So the two terms being the probability of being at xk and then the probability of then transitioning to xk plus 1, given that we started at xk, is going to be equal to the probability of being at xk plus 1 and then transitioning to xk. Okay, so the amount flowing back and forth are equal. Okay, so we have detailed balance. When we use the transition probabilities prescribed by the Metropolis Hastings algorithm. Okay. So we have detailed balance when we use the transitions probabilities prescribed by the Metropolis Hastings algorithm, and the target PDF is our stationary PDF. Is the stationary distribution. Okay. All right. Is that good? So this is so this just kind of shows that the Metropolis Hastings algorithm, it works out. Okay, that when you set up the transition probabilities this way, so that that you're using the ratio of your proposed value versus your current value as part of determining whether you're going to accept it or not, then the stationary distribution will be equal to your target distribution. Okay, and from ergodic theorem, we know that if you run a chain long enough, the chain will produce values according to its stationary distribution, and therefore running a chain according to the Metropolis algorithm will produce values that come from our target PDF. Okay. Says that a irreducible and aperiodic chain will eventually converge to its stationary distribution. Okay, and we showed that show the stationary distribution of a chain created by the Metropolis Hastings algorithm. Is equal to the target PDF. Okay, so running a Markov chain this way will produce values from our target distribution, which is what we want, right? And then, once you have values from your target distribution, then you can do Monte Carlo integration and Monte Carlo estimation and things like that, okay? Once you have values from your target distribution, integration or estimation. Okay, yay. That's so it's, I don't know, kind of a big deal. And we showed that the Metropolis algorithm and Metropolis Hastings algorithm is particularly useful because you don't have to calculate the normalizing constant that's often present in Bayesian methods. All right. Okay. Let's see. You guys have a midterm in a week, right? 7th week Wednesday. And then we don't have class on Monday. It's Veterans Day. So we have class on Friday, then you have a long weekend, and then on Wednesday you'll have the midterm exam. So I'll probably cover details of the midterm exam on Friday. Let's see. I guess with our remaining time, we've got about 10 minutes. I don't know, I can answer questions. I want to emphasize, so I don't know, people complained that the midterm was like too mathy, but it's paper, right? I can't do code and stuff. I mean, it's hard to do a bunch of code. But let me just kind of pull up our first, your homework assignment here. And let's take a look at this this first Bayesian problem. Okay. And I'll just tell you, there's going to be a Bayesian mathy problem, okay, on the midterm exam. And so I think problem 1 is a good one to study. Of course, it's not going to be exactly this, all right? But you should be comfortable with the idea of doing some Bayesian analysis using a conjugate prior, okay? So anyway. Bayesian inference with a conjugate prior, okay? And I think I said this, but what's a conjugate prior? The conjugate prior is just a PDF, okay? It's a probability distribution, PDF, probability distribution that has nice mathematical properties for a particular likelihood. Just have it there. Okay. So here I said the gamma distribution has a PDF of the form this. Okay. So this is homework for number 1. Okay. So the gamma PDF for f of x given parameters alpha and beta. All right, you've got beta to the alpha. So you'll often have a semicolon to separate, to indicate, I guess, parameters. It still is kind of the idea of given, but you might have seen, like, you might be accustomed to given being a vertical bar, and that's true. But you'll often do given with a vertical bar for, like, if you've got like a multivariate distribution and one of the variables is conditioned to a certain value, and then you often use semicolons to indicate that the parameters are equal to certain values or something like that. Okay, so we've got this, and this is beta to the alpha, the gamma function of alpha, and x is alpha minus 1, and you got e to the negative beta x, okay? And then, we often get scared of the gamma function and all of this, but this part only serves as a normalizing constant, right? So this part is just a normalizing constant. So the only part that's really of interest to us are the things that have x terms in them, okay? So, this stuff depends on x. Okay, and then over here we have an exponential distribution. Why am I, how do I scroll? Okay, and then we have an exponential distribution. So this is going to be our prior. Okay, and then the values in our data come from an exponential distribution. And the exponential distribution is determined by the parameter lambda, your rate parameter, and this is going to be lambda e to the negative lambda x. Okay, so that's what we have here. And then, and I said, okay, so the gamma distribution is our prior. Our values come from the exponential distribution. And so here, we're going to look at how many customers arrive, within a certain time and things like that. And we want to come up with some kind of estimate here, right? And so I think we set up our prior distribution. Our gamma prior has alpha equal to 8 and beta equal to 1. Okay, so right now, our prior distribution for lambda comes from gamma with alpha equal to 8 and beta equal to 1. All right, and that's what this thing looks like. Okay, so this is our prior distribution on lambda. We're saying the rate parameter lambda can be anything, in this distribution. Might be as something like this, okay? And we have data points y, okay? And then we have data, the vector y, which consists of 0.131, 0.078, Okay, so you got a bunch of terms for your y. And so what we need to know, okay, so we want the posterior distribution of lambda given our data y. Okay, so we want the probability of lambda given y, and this is going to be equal to our data given the lambda, this is the likelihood, multiplied by the prior, divided by the marginal probability, okay? But we're going to just ignore that marginal probability on the bottom, and we're just going to say it's going to be proportional to the likelihood times the prior, okay? And if we can figure out, and if we can get a gamma distribution, or find this in the form of some PDF we recognize, then we can pick out the values accordingly, and then we don't have to worry about figuring out the normalizing constant ourselves. Okay. All right. So the likelihood, okay, the likelihood term of y given lambda, this is going to be, because each value is independent, this is going to be the product of the density values for each y, okay? So this just becomes the product, basically I equals 1 to n of your PDF, in this case, f of y, yi given lambda, okay? And so this will just be the product of lambda e to the negative lambda y sub I. Okay, so it's going to be lambda e to the negative lambda 0.131 times lambda e to the negative lambda 0.078 times lambda e to the negative lambda, whatever the next value is, right? 0.297 times ... Okay? So this, I feel like this is I don't know, big help here, right? So this is, you're gonna, simplify this. And then, so you get something, this is gonna be in the form of, simplify this, and then and that's going to be your probability of your y given your lambda. Oops, the y given lambda, and then is going to be equal to whatever you get simplified there, and then again the prior distribution is in the form of gamma. Okay, beta to the alpha, gamma of alpha. X to the alpha minus 1, e to the negative beta x, okay? So this is going to be lambda to the alpha minus 1, and e to the negative beta times lambda, right? Because this is the prior distribution of lambda, not x, okay? So you have this, and then you multiply the two together, multiply basically the likelihood by the prior, and then see if you can kind of identify new parameters of alpha and beta to use in the resulting PDF. Okay, we'll stop here for now. On Friday, I'll talk more about the midterm exam on Wednesday, and then we're going to start, I think, an exciting application of the Metropolis algorithm. So we'll take a look. Okay.